Hi everyone, welcome back to AWS Julie. Let's continue on our new playlist covering the fundamentals for the AWS Certified Machine Learning Engineer Associate Exam. And let's continue with Domain 2 and talk about training and refining models. So we have talked about what neural networks are and how they work once they have been trained. So under 2.2, I want to talk about how we train a neural network using loss functions, gradient descent, and finding the minimum. We take our data set and design how we want the neural network, such as how many input neurons are needed, how many output neurons, and a design of the hidden layers. And then we set it to work and to train itself to be able to detect cases of, for example, the classes we input into it. So let's dive deeper and talk about how a neural network learns to do that. And this process is similar to others we've already talked about in this course. We have talked about how machine learning works, and in many cases it starts with a random state. Then it calculates a loss, and then the algorithm tries to reduce that loss using stochastic gradient descent or a derivative of that. Then the loss is calculated again, and then with the loss value, it tries to reduce that loss again. And then it continues in a loop to reduce the loss or reduce the cost of loss. And then once we are happy, we say, that is good, and we use that model. At a high level, this is how we train many of the algorithms we have looked at so far. And we saw this in a previous lesson with the loss function and gradient descent inside the linear regression lesson. So let's look at how this works in a neural network. The algorithm takes the input values to the input neurons, and we get activation numbers from the output layers. Then it compares the values that it gets out of the network and compares those values to the ideal values that we would like to see. And then using these values that we want to see to get our loss function by looking at the values that come out of the network and the value that we are looking for. We square those values and then sum them together, and we get a total cost. For this image, the network has been configured with the weights and the biases, and it has now defined how to calculate a loss. This is only one way. There are others, but we are looking for the loss with the lowest value. Then this strategy is used to train all of the data, and then it calculates an average cost. All of the data is inputted into the input neurons, and then we take the average cost, which is calculated by every sample divided by the number of samples that we have in the data set. At this point, you can take this information and adjust the weights and biases to get a lower cost using a calculus equation and performing gradient descent. And each step down the gradient, the algorithm reassesses where it is, performs some calculus to calculate the gradient, and figures out where to go next. So at a high level, we input all of our data into the neural network. It then calculates the average cost for all of that data. Then it calculates the gradient of where it is currently in the loss function. Then we use that to adjust the weights and biases in all of the network to reduce the loss the next time around. And the updates are pushed back through the network with back propagation. And this process, the process of passing in the updated information, is called an epoch. So in previous lessons, we mentioned different ways we can prepare the data for the training process. We've talked about training and testing data splits to have our model trained on the training data, and then evaluating that model using the data it has never seen before. In that previous lesson, we mentioned an alternative to splitting your data between training and testing data, and that alternative is cross-validation. K-fold cross-validation is a process where we can use all of that data to test our model without removing or splitting off any of our data. So we use all of the training data to train our model, and then all of that data to test the model. K-fold cross-validation is a method that works well with sequence data and can use sequence events in the right order. It uses every data sample to train and test the model. It is often used when you need to produce multiple candidate models, measure the performance of the multiple models, and then you can choose the best model. It helps you gain better metrics and insights from the available models. And remember, we mentioned earlier how we train, test, and split does not work well with sequence data, but K-fold cross-validation works well with sequence data. Train, test, split can be problematic also for small samples of data, and if you have issues sourcing enough data to train and test, because when you split part of your data into your testing data, you have even less data to train your model. But K-fold cross-validation can help with sample data sets and sequential data. Here's a question. What is the K in K-fold cross-validation? Is it a number just like in the K-means algorithm and the K-nearest number? No. In K-fold cross-validation, K is the number of folds you will create in your data set or the number of sets you split your data into. And in this example, we have 7 different folds. And then the data is presented to the training process over multiple iterations. So in this first iteration, we have the first portion of our data set as the testing data. And this looks similar to our train, test, and split. The difference is that when we run the second iteration, we move the test data set to be in the next fold or section of the data. And then the other data is used to perform training, and now the second fold is used for testing. And this process continues until we reach the end of the data set. And at the end, we have trained our model multiple times, using all of the data for training and all of the data for testing. And you can compare the performance of multiple models. So K is the number of sections you split your data into, and then you complete cross-validation by iterating through all of the different combinations of the data set. And 7 is a good number for K-fold validation. The higher the K is, the longer it takes to process, train, and test the data set. Let's continue on with Task Statement 2.2, training and refining models, and let's talk about regularization, because we have to take regularization into consideration when we are training our data, and it is a remediation for problems that occur when we are not training our data effectively. And we will dive deeper into regularization later on in the course when we're talking about how to troubleshoot our models. But I did want to introduce it here. So what is regularization? Well, it is when we are desensitizing the algorithm to the data to prevent overfitting. Remember, overfitting is when our model fits our training data so well that it does not generalize and fit the real world or the testing data. Regularization can also be used if you have a data set with more features than samples. Let's say that you need to create a model with a data set that is wide with 100,000 features and 2,000 samples. And I've seen this a lot in the medical scenarios with lots of data about a patient's health and only collected data from a few thousand patients. And this can be problematic in linear regression. In a linear regression, you need to have at least one sample for each feature to find the hyperplane in a multi-dimensional space. So for example, if you have 3 features and 2 samples, if you plot those in a 3-dimensional space, you will not have enough information to map a hyperplane because you would have 2 points, and you could then put in your plane into different locations that go through those 2 points. And if you scale that up to 100,000 features and 2,000 samples, you still do not have enough samples to complete an effective linear regression. And regularization can help solve this problem by desensitizing features in the data set by adding regression penalties. And then you can use cross-validation with this to find the best regression value. And remember from the beginning of this course with this linear regression model, let's say that our 2 data points in green are our only 2 points. So where do you draw that line? Well, we would have to put the model on top of the 2 data points because it is the only linear regression line that fits. And at this point, the sum of squares is 0, and it would be the minimum of the gradient descent. And we can see that there are other data points, and this linear regression model is not working well, and the model is overfit to the small data set. It has low bias and larger variance. And in the real world, you need to get more data. But let's talk about how regularization can help for this simple example. But remember, in the real world, you need more data. Regularization adjusts the coefficient, and we adjust the angle of the line until we find a line that it fits better with in the testing data. And the way it works is that regularization adds a penalty to the formula that draws that line in order to reduce the angle of that line and desensitize height to food by adding bias, which causes it to reduce variance, and it can generalize better. You can use cross-validation to try different values to find a point at which it works better. Let's also talk about the methods of regularization. There is L1 and L2, and both work in a similar way, but they have different use cases. L1, also called lasso, can help to eliminate statistically useless features in our data set, such as a person's name or identification number. It applies a penalty of 0 to the feature, which essentially turns that feature off and eliminates the feature. L2 regularization is known as ridge regression regularization, and it can reduce the influence of features. It does not reach 0, but reduces that influence. And this is used when there are more features than samples. And an important part of training and machine learning models is hyperparameters. And we've mentioned hyperparameters a few times already. Hyperparameters are how we control a training model, kind of like tweets or knobs that we can control to how a model trains, improve model performance, and the model outcome. But all of this depends on the algorithm we use and the implementation of that algorithm. I just mentioned that we've discussed hyperparameters throughout the course so far. Can you think of a few examples of hyperparameters that I've mentioned? Well, we just mentioned epoch count, but there's also batch size, learning rate, and regression type. So remember when we pass it our data, the algorithm completes some calculations and comes up with numbers, weights, bias, coefficients, and so on, and then creates a model. But the algorithm comes with values inside the algorithm which influence how the calculations of weights, bias, coefficients, and so on actually work. And those values inside our algorithm are the parameters. But there are also hyperparameters inside the algorithm that we can set up to help influence how the model trains. Epochs are the number of times the data is passed into the training process, and as the data is passed into the algorithm, it will continually refine the values and parameters that it calculates and give us a model. Batch is the size of a subset of the data that will affect the parameters of the model and the number of samples we send in each time. And this is common in the real world, not in our simplified examples throughout this course, but batch will pass in data subsets instead of passing in all of the data at once, and will update its weights, bias, coefficients, and so on each time it processes a batch data subset. And this can be faster, and the data is batched by the number of epochs. There is also a mini batch where the batch size is greater than 1, but less than the complete data set, and they can be distributed among different processors or machines. Let's also talk about learning rate or step size, which is how far to step when optimizing and how fast we'll find that minimum point. If you use a learning rate that is too big, then you may miss the bottom and end up bouncing around the actual minimum. If you use a learning rate that is too small, It will take a long time to train, and this may end up being useful because of the extended time to train the model. Let's continue with task statement 2.2, which is to train and refine models and talk about data shuffling in AWS. Remember, we've talked about randomized data, and shuffling your data is important because the stochastic gradient descent algorithm is influenced by the order of the rows in the training data, and the training data helps the algorithm to converge on the optimal solution sooner. The stochastic gradient descent algorithm also makes sequential passes over the training data, so the number of passes parameter controls the number of passes that the algorithm makes over that training data. More passes result in a model fit that fits the data better if the learning rate is not too large, but the benefit diminishes with an increasing number of passes. For smaller data sets, you can significantly increase the number of passes, which allows the learning algorithm to effectively fit the model more closely. For extremely large data sets, a single pass might suffice. If you have many input features, the number of possible patterns in the data can result in a large model. Large models have practical implications, such as requiring more RAM to hold the model while training and when generating predictions. You can reduce the model size by using L1 regularization or by specifically restricting the model size by specifying the maximum size. Note that if you do reduce the model size too much, you could reduce your model's predictive power. So before we move on, let's talk about optimizers. Optimizers are one of the hyperparameters that we can set our algorithms as we train our models. We also talked about optimizers before in regards to the loss function under stochastic gradient descent lesson, but also in relation to linear regression. And a few examples of optimizers are gradient descent, stochastic gradient descent, atom, and many others. An optimizer is how the algorithm finds its way down the hills. Under the hyperparameters of learning rate, we talked about stochastic gradient descent and how it can help in an earlier lesson. A loss function is trying to calculate the loss of what the machine learning algorithm has figured out through the iteration or epoch of training of what it found and what it was expecting. So the algorithm has some labeled data, and it knows what it is trying to get to. It knows how far it has gotten, and the differences between the two is that loss. And it manipulates the weights and biases for a neural network, for example. It will adjust and change those over time and decrease that loss until it gets to a minimum. Stochastic gradient descent uses the individual data samples to step down instead of using the entire data set to step down. But what happens if one of those data points is skewed? Well, it can throw off the algorithm, throw it off track, or cause it to go backwards and step up instead of stepping down. So what is the solution here? What can we do? We can add in optimizer values into the stochastic gradient descent algorithms called momentum and acceleration. This helps the algorithm to get tabs on the direction it is stepping and the overall momentum to the movement. And to find the loss function faster, we can use another optimizer called adaptive gradients. And instead of using momentum and acceleration applied in general to the entire movement, adaptive gradients looks at the values in the direction of the dimensions of that data to add more focus to the direction it will go. So when we have the momentum and acceleration set for each individual dimension of the data, what is that called? That is called an atom optimizer, and it is the current best optimizer you can use for generic data sets in machine learning. But the optimizer that is best for your scenario and data set depends on what works best or gives you the best performance. And we'll go deeper into performance under Domain 3 in those upcoming lessons. But let's continue on with task statement 2.2, training and refining models. And we've mentioned several times that machine learning is a huge topic, and we could spend a long time tweaking training and testing. And we've talked about how we can use automatic hyperparameter optimizations to set ranges on the parameters and then get machine learning to train machine learning and define that optimal value for the learning rate. When using grid search, hyperparameter tuning chooses combinations of values from the range of categorical values that you specify when you create the job. But only categorical parameters are supported when using the grid search strategy. When using random search, hyperparameter tuning chooses a random combination of values from within the ranges that you specify for hyperparameters for each training job it launches. Because the choice of hyperparameter values doesn't depend on the results of the previous training jobs, you can run the maximum number of concurrent training jobs without affecting the performance of the tuning. For Bayesian optimization, hyperparameter tuning uses an Amazon SageMaker implementation of Bayesian optimization. When choosing the best hyperparameters for the next training job, hyperparameter tuning considers everything it knows about the problem so far. Sometimes it chooses a combination of hyperparameter values close to that combination that resulted in the best previous training job to incrementally improve the performance. This allows hyperparameter tuning to use the best known results. Other times, it chooses a set of hyperparameter values far removed from those it has already tried, and this allows it to explore the range of hyperparameter values to find new areas that are not yet well understood. The explore and exploit trade-off is common in many machine learning problems. Hyperband is a multi-fidelity based tuning system strategy that dynamically reallocates resources. It should only be used to tune iterative algorithms that publish results at different resource levels. Hyperband uses both intermediate and final results of the training jobs to reallocate epochs to well-utilized hyperparameter configurations and automatically stops those that underperform. It also seamlessly scales to using many parallel training jobs. These features can significantly speed up hyperparameter tuning over random search and Bayesian optimization strategies. What is an example of when you would use Hyperband? Hyperband can be used to tune a neural network for image classification, which publishes accuracy metrics after every epoch. Hyperband with early stopping can be used for training jobs that can be stopped early when they are unlikely to improve the objective metric of the hyperparameter tuning job. This can help reduce compute time and avoid overfitting your model. Hyperband uses an advanced internal mechanism to apply that early stopping. Let's jump back to a previous lesson and look at the overview of our SageMaker stack. One option is you can bring your own container. Another option is to use script mode and present your own code, usually with one of the machine learning frameworks. SageMaker does not use containers to scale, but instead as a method to deploy code, binaries, and the environment to Amazon EC2 instances running inside AWS. And you can create your own custom containers with your own image, Docker files, and more, but you have to conform to the standards that SageMaker expects to see. And SageMaker will manage the deployment and lifecycle along with the infrastructure for you. Let's move on and let's talk about transfer learning. So far in this course, our examples have been two-dimensional and with smaller data sets, but you can understand that it takes a long time to train a model, such as a large neural network, and then to process all of the data in the real world is millions of calculations per epoch. This process of fine-tuning and training a pre-trained model on a new data set without training from scratch is known as transfer learning. and it can produce accurate models with smaller data sets and less training time. You can accelerate the learning for some types of models using transfer learning and use a pre-trained model as your starting point for the training of a new data set. You can create your own pre-trained sets or get them from the internet. The generalized model from the generalized data set can be transferred into your training process with your new data set. Then when you train your model, the algorithm already knows some information and understands what it needs to do. Then it just needs to figure out how those elements map to your new data set. As machine learning and artificial intelligence evolves, we have seen different types of machine learning models. Ensemble modeling has become popular, and you can train, optimize, and deploy your custom ensembles using SageMaker. Ensemble models are a machine learning approach to combine multiple other models in the prediction process. Ensemble learning refers to the use of multiple learning models and algorithms to gain more accurate predictions than any single individual learning algorithm. What is a use case for ensemble learning? Cybersecurity, fraud detection, remote sensing, predicting best next steps in financial decision making, medical diagnosis, and even computer vision and natural language processing tasks. Ensembles are categorized by the techniques used to train them, their composition, and the way that they merge the different predictions into a single inference. Although several libraries and frameworks provide implementations of ensemble models, such as XGBoost, CatBoost, or Scikit-learn's Random Forest, you could also bring your own models and use them as stacking ensemble. And instead of using dedicated resources for each model that's dedicated training and tuning jobs and hosting endpoints per model, you can train, tune, and deploy a custom ensemble with multiple models using single SageMaker training jobs or using a single SageMaker training job and a single tuning job and deploy to a single endpoint, thereby reducing possible costs and operational overhead. You can reduce the model size by altering data types, pruning, updating feature selection, compression, and more. And Amazon SageMaker has many features, tools, and services that helps you create and store information about the steps of machine learning workflow from your data preparation to model deployment. With the tracking information, you can reproduce the workflow steps, track model and data set lineage, and establish model governance and audit standards. And there's also services, tools, and features to help you manage your model versions for repeatability and audit. You can catalog models for production, manage model versions, associated metadata, such as training metrics with a model, manage the approval status of a model, and deploy models to production and automate model deployment with CI/CD. Now I'm going to stop this here. I was hoping to get through test statement 2.3 and wrap up domain 2, but this one was pretty long. So in the next lesson, we'll continue on with test statement 2.3 and the fundamentals you need to know. And test statement 2.3 is analyze model performance.